real exam questions. This is question 11 and deals with slab design and yield lines. Determine the reinforcement of a triangle balcony with fixed ends on the two sides of 7 meters. The fixed end bending moment is double the field moment. The slab is loaded with a uniform distributed load of 14 kilonewtons per square meter in ultimate limit state persistence. The effective depth of the slab is 120 millimeters. Looking at the problem, we see that this will be the axis of rotation, and this is the axle of rotation. So where the slab is fixed, there is a yield line. The same happens on this side. And when the two axes of rotation cross, then the yield line starts. And because of symmetry, we take it at 45 degrees. Or we use the 30, 45, 60 degree rule. The plastic bending moment in the field is M, and on the fixed end supports, it's 2M. We can calculate the work done by the external forces, which is Q, 14, times the surface or the area of this portion, which is 7 times 7 over 2, and then half of it. And the mean deflection of a triangle is delta over 3. Of course, for the other side is exactly the same. And the total gives you 343 divided by 3 kilonewton. Notice that because of complete symmetry, it's all triangles. So in fact, E, you can find it immediately by taking the total load on the triangle and multiply it by delta over 3. The work done by the internal forces. Then we have, this is the plastic bending M projected so this on this axis of rotation. So the length is 7 over 2, M times 7 over 2. And the angle of rotation is, of course, that's here delta divided by this distance, which is 3.5. So that's what this is stating. We have this bending moment projected on this axis, but we have also this plastic bending moment projected on this axis. That's where there is a 2. And then for the fixed end supports, we got 2M projected on this axis means 7 times the rotation, angle of rotation, it's delta divided by 7 over 2. And we got that 2 times on both sides. So this is this fourth of the equation. In total, we got 10M. Now, E is equal to D, so we can get M out of it. And M is then 11.43 kilonewton meters. Just to avoid confusion, this is kilonewton meter. This is the bending moment of a slab, which is written with a small letter M. That's why I made M accent for not making a mistake to identify one of those. The bending moment is 11.43 kilonewton meter per meter. The reinforcement needed for that to cover this bending moment is the bending moment divided by the lever arm, which is 0.9 times 120, and divided by the yield strength of the reinforcement. We add 10% to that because we are working with an upper bound method. 10 to the power 6 is just to convert it into the right units in Newton and millimeter. So we have 268 square millimeter per meter. You can do that with a diameter 8 every 188 millimeters. Then you arrive at 267, which is okay. But the maximum distance between two reinforcement bars, where the bending moment is the highest, the biggest, it's 1.5 times D. So the maximum distance between two rebars is 180. We are here at 188, so we have to correct it and put diameter 8 every 180 millimeters, which gives you 279. You can also look at a diameter 6. A diameter 10 will also have this problem that is not complying with SMAX. We take a diameter 6 and we find diameter 6 every 105 millimeters will be okay. So practical reinforcement, we will say, of course, diameter 6 at 10 bars per meter is 283. That's the reinforcement, the bottom of the slab. Top reinforcement, we know that the bending moment top of the slab at the supports, it's 2m, so that's 22.86 kilonewton meter per meter. The reinforcement needed is again the bending moment divided by the lever arm and the yield strength of the steel, augmented by 10%, gives you 535 square millimeters per meter. You can convert it in a diameter 10 every 147 millimeters and gives you 534, which is okay. The diameter 10 every 143 millimeters is 549 square millimeters per meter. And the 143 comes, of course, of the 7 bars per meter. This is not very practical in use, but you can put 7 bars per meter. But the distance between every bar is a strange number. But this is still okay. This can be done. Then you have a diameter. You can also look at a diameter 12 at 211 millimeters. This gives you 536. Yeah, to make it practical. First of all, this is bigger than SMAX. So you can only take 180 millimeters. So if you take diameters 12 elder 180 millimeters, you have 628. So you see, this is much more than the needed one. So to avoid this, we will stick with the diameters 10, 7 per meter. And this is then the practical reinforcement. So top reinforcement is diameter 10, 7 per meter. And the bottom reinforcement is a diameter 6 at 10 per meter.